The very last one that we need to go through is the osmotic pressure. If you have a U-shaped tube, and then between this tube you put a semi-permeable membrane, then membrane only allows your solvent to pass, but doesn't allow your solute to pass. In the beginning, they have the same height. But as time goes by, what's going to happen is that the water molecule is going to go to the side that have more solute, because the nature always trying to make things balanced. If you have too high concentration, the water is going to go there to dilute that concentration. So what happens in the end is that this goes down, that goes up. And the height difference between the two is so-called the osmotic pressure. Since the water trying to go to the side to dilute the solute concentration, if you add in more solute, the height difference between two ends will become larger and larger. And the equation you want to use is pi equals to m times r times t, where pi is the osmotic pressure, n is the concentration term, molarity, which is number of mole of solute per liter of solution. Again, it has to be this unit. If you use other concentration unit, you got the wrong number. R, in this case, is a gas constant. It's very important that you use the correct R, 0.08206. And you have the unit of liter ATM, temperature in Kelvin, and mole. Many of students use the 8.314, which has the unit of joule per mole. This is actually not the R you want to use. Temperature has to be in Kelvin. The pressure has to be in ATM. So let's look at one example. A solution contains 35 gram hemoglobin dissolved in water. From 1 liter solution, exert an osmotic pressure of 10 torr at 25 degrees C. Find out the molar mass of the hemoglobin. Question-wise, looks very complicated, right? But what's the keyword? So once you see this keyword, there's actually only one equation, right? Pi equals to mRT. What's T? Temperature in Kelvin. So it should be 298, right? R, make sure you use the correct constant, 0.08206. Pi, osmotic pressure, right? Do you have the information here? What's the unit of your pi? ATM, right? What's the unit in your question? Torr. Do you know how to convert torr to ATM? 1 ATM is equal to 760 torr. So you know your pi is 10 divided by 760. So this will make it become ATM. So now, what is the molarity? We know it's actually a number of mole per liter, right? So we know it's 1 liter, so you know liter just equals to 1. And the number of moles defined as the mass of your solute divided by the molecular weight. What's the mass you have here? 35, right? And then you want to know the molecular weight. Then you can solve that the molecular weight is equals to. Okay, so let's talk about application. Osmotic pressure actually play an important role in the medical solutions. If today you have a membrane that is semi-permeable, that only allow your solvent to go through, but doesn't allow your solute to go through. If that is the situation you have, then the osmotic pressure is going to be generated. It's actually a red blood cell. If everything's normal, we call it as an isotonic situation. So in this case, the concentration inside and outside your red blood cell is more or less the same. The water just go freely in and out of your cell, and then the cell looks normally. So we call this situation as isotonic. But if today you put your red blood cell into a solution that has very high salt concentration. So right now you have more salts in your environment than inside the cell. The reason that you see the osmotic pressure is because the water will always go to a direction that is going to make the inside and outside concentration become similar. So outside the cell right now you have so high concentration of salts. Therefore, the water inside your cell wants to go out. And in that case, you will see the cell start to shrink. So under this case, we call it as hypertonic situation. In the opposite, if you just put your cells into a solution that only contains your water. So right now, inside your cell, you have a very high salt concentration. Outside is just water. So the water from the outside will try to get into your cell. It will actually make your cell start to swell, eventually break the cell. And for that case, it's so-called the hypotonic situation. So the other interesting one, so there are actually a couple, I will just pick two for today's lecture. The other thing that you will see this application very often is actually at home. Many of you must have this reverse osmosis water filtering system, right? Typically, you will see the filter, and then you're going to see a water tank. If you have this, but you never actually look at it, go back home and look at it. That is actually the tap water coming out from your faucet. Some of the water will go to these sides, but because there are many salt on the right-hand side. So at a certain point, the water won't go to the left-hand side anymore. You're going to see these things start to form the osmotic pressure. What your filter do is actually they're going to exert certain pressure, push the things to the left-hand side. And these things will eventually go to the tank and get stored. Because the force it exerts from your setup is actually a constant. Okay, that means actually they can only push certain amount of water to the left-hand side. So what they do is actually there'll be actually a tube that fit in the tap water constantly and bring out this water, the salty water out too. So they can make this process continuous. So let's actually the applications of osmotic pressures. Okay, so these Van Hoff factors will actually play important roles in your homework. The Van Hoff factor is basically equivalent to the concept that you learned previously. When you calculate the normality, we introduce a concept called the number of equivalent. For the non-electrolyte, your Van Hoff factor, which always written as I, the I is always equals to 1. But for the electrolyte, it changes. So right now the thing is, what is non-electrolyte, what is electrolyte? Whatever substance that can actually generate iron in your solution when they dissolve, those things are called the electrolyte. If it cannot, then it's non-electrolyte. So the commonly seen electrolyte including three things: salt, acid, base. If you look at this table, it will give you a better idea. Glucose is not a salt, it's not an acid, it's not a base. It's just a molecule. Once it dissolves in waters, it did not generate ionic species. So we call the glucose as non-electrolyte. So if it is non-electrolyte, then its Van Hoff factors is going to equal to 1. Then we can start to talk about the electrolyte. So all the things I highlight here, they are actually all electrolytes. What is HCl? Acid, right? Is acid an electrolyte? Yes. Once it dissolves in water, it's going to become H plus and Cl minus. Even though you just dissolve one HCl, you produce two charged species. So that two is so-called the Van Hoff factor. Another example, NaCl. What is NaCl? Salt, right? It's salt electrolyte. Yes. What will it become once it dissolves? Na plus plus Cl minus. So how many charged species if one NaCl dissolve can generate? 2. So the Van Hoff factors for your NaCl aqueous solution is 2. I found students actually got confused about these things. MgCl2. It is actually also a salt. So once it dissolves, what are you going to get? Mg2 plus, good, and then plus Cl minus and 2. How many charged species you have generated? 3, right? So the Van Hoff factor is 3. I will leave the remaining for you to practice. Okay, but the key thing is what? Key thing is actually, can you recognize the acid, base, and salt? If you can, that's the first step, right? You know it's actually electrolyte. Van Hoff factors cannot be 1. Then what is the Van Hoff factors? Then you actually write out the dissociation equations. So you will know how many charged species will be generated. Once you have these Van Hoff factors, why does it matter? Okay, it actually matters regarding to actually associate with your collective property, right? Because when we talk about the collective property, it actually only matters about number of particles inside your solutions, right? So because it is electrolyte, okay, even if you're just throwing one, effectively you actually produce two molecules. So you need to correct for that. So in all the equations that you have, like delta TB, delta TF, or the osmotic pressure, you need to actually add in the Van Hoff factors in the front. So you can actually calculate the proper collective properties. We are going to go through one example. Find out the boiling point of 0.9N FeCl aqueous solution. Boiling point is actually a keyword. So for the boiling point, this will be the go-to equations. Delta TB equals to I times K times M. And then, of course, there's another one you need to know is actually the boiling point of your solution is going to equal to the boiling point of your solvent. Plus or minus your delta TB? Plus, right? Plus your delta TB. So you know this equation is going to give you the correct answer. So what is your solvent? So how do you know it's water? Aqueous, so it's water. Boiling point of water, 100 degrees C, right? How do you calculate your delta TB? We know it's actually I times your Kb times your concentration of your solute, right? So your I for your FeCl3. FeCl3 is electrolyte or non-electrolyte? Electrolyte, right? So once it dissolves, FeCl3 is going to become Fe3 plus, right? Plus 3Cl minus. Therefore, I equals to 4. How about your Kb? Who's Kb you should actually looking for? Water, right? So if you go to your textbook, so you'll find that Kb is equals to 0.52. When you do your homework, it will be provided. Then you need to calculate the concentration of your solute. What's the concentration of your solute? 0.9, right? Then you will find out the final answer is 101.872 degrees C.